Hello, good day, and welcome to our lesson. So today we want to talk about the Doppler effect, all right? So we are defining it as the apparent change in observed or detected frequency as a result of the relative motion between the source of sound and the observer or the listener. So basically, why the observer or the listener? Because we talk about the Doppler effect in terms of two things: either the sound. So if it is the sound, obviously we are talking of the listener, or the light. So when you talk of the light, we talk of the observer. That's why we are saying either the observer or the listener, right? Or we can define it also as the change in frequency or pitch of sound detected by a listener, because the sound source and the listener have different velocities relative to the medium of sound propagation, right? So basically we are saying this is then the variation that tends to occur in the frequency heard by the listener or detected by the listener due to the motion or the relative motion between the source and the listener, right? So we can best explain this phenomenon or this effect using these diagrams, which are explaining the waves or the wavefronts that tends to be emitted when sound is emitted, of course. So we are basically saying sound is emitted in terms of waves. So what happens is that if the source of sound is stationary, these wavefronts tend to be emitted such that they are evenly distributed, like the way we are seeing here in the first diagram, right? It's showing us that the wavefronts are evenly distributed, showing us the distance between them is somehow the same, or it's equal. They are equally distributed, right? The distance that lies between these waves, the distance between the waves or the wavefronts is known as the wavelength. That's the wavelength apparently, right? And it is given the symbol lambda from the Greek alphabet, right? So now, what happens is that, of course, this wavelength, it varies inversely with the frequency. So they are given by the formula. Frequency is equal to a velocity over lambda, the wavelength, where frequency, of course, is defined as the number of waves that are made per second, or the number of cycles made per second. Right. So basically, it is the same. We are seeing here where is the wavelength, right, from each peak to each peak. This is now representing the wavelength. So that marks our wavelength. At the same time, this is also marking our wavelength, right? The lambda. Okay. So it's given by that formula. So from this formula, we can actually see that frequency varies inversely with the wavelength lambda. That's what it means there. They are inverse variations, right? However, it so happens that if the source of sound is moving towards a certain direction, the wavefronts tend to compress towards that direction. This is what results, right? So automatically it means as the source of sound is moving towards this direction, it means the wavefronts are compressing towards that direction. So if I have a listener at this position here, let's assume we're having a listener at this position, and then we have another listener perhaps at this position, right? Or the very same listener is now at this position after the source of sound has passed the listener, right? It automatically means, so let's call this one observer B, let's call this one observer A. So definitely it tells us, or it shows us that observer A shall hear a higher frequency than observer B. Why? Because here, where the waves have been compressed, or where the wavefronts have been compressed, it's evident that the wavelength is now very short. The wavelength is short, and apparently wavelength varies inversely with the frequency. It means there is now a greater frequency this side than this side. So on this other side, since the wavelength is greater, it's also telling us that the wavelength here and the frequency here is short, is lower. So the observer B shall have a smaller frequency. The frequency of the listener B shall be smaller than the frequency of the source. But the frequency of observer A shall be greater than the frequency of the source. So it must always come to our attention that for as long as we are explaining, or in what we are explaining regarding the Doppler, we are simply saying that if the source of sound is moving towards the listener shall tend to hear a frequency higher than the frequency of the source. However, let's go back to our source if it is stationary, which means we are saying here our source here is stationary. Right, but however, now it's moving here, and as it is moving, we can see that the wave fronts are compressing towards the direction of its motion, right? So what happens then to the listener here when the source of sound is stationary? It means the frequency of the listener shall be equal to the frequency of the source. They shall have the same, the equal frequency due to the evenness, of course, of our wavelength, right? So there is obviously the same frequency, the frequency of the listener and the frequency of the source, right? So that will not be the case now when the source is moving towards a certain direction. So we are witnessing also due to the compression that is taking place to the wave front. Now, this is what the Doppler effect specifically is talking about. So all this generates an equation, which is known as the Doppler equation. So let's now talk about the Doppler equation, how we can understand it, right? It says that FL is equal to V plus or minus VL over V plus or minus Vs multiplied by Fs. So this is our equation, right? So what the equation says, of course, where FL is the frequency of the listener, this is the frequency of the listener, and V is the velocity of sound in the medium that it is traveling in. So oftentimes we use the medium of air. So this becomes the velocity of sound in the medium, or when the medium is air, in the medium of air, right? Of course, this marks now the velocity of the listener, and this marks the velocity of the source, right? And then, of course, that's the frequency of the source, right? When do we add and when do we subtract? That's the other critical thing to know, right? When do we add and when do we subtract? So we have to understand that we shall add when the listener is moving towards. So when the listener is moving towards the source. And when do we subtract? When the listener is moving away. That's when we subtract. Right, how about here? When do we add and when do we subtract? We subtract when the source is moving towards, and we add when the source is moving away. Sometimes it's a little bit difficult to understand what exactly is happening. So this equation is generated from what we have been discussing here, to say we need a greater frequency when the source is moving towards the listener. So the frequency of the listener shall be greater than the frequency of the source. However, the frequency of the listener shall be smaller than the frequency of the source when the source is moving away from the listener, right? So automatically here, for us to get a greater frequency, it means the numerator here has to be bigger, which means this whole fraction that we are having here, this whole fraction, the numerator has to be bigger, V plus VL. It has to be bigger. How can it be greater? By adding. But the denominator must be kept as small as possible, because comparing any two fractions, let's talk about, for example, 2 over 5 and 2 over 7. 2 over 7 is a small value. It's a smaller value than 2 over 5. Why? Because as long as the denominator becomes a bigger value, it is telling us that the whole fraction becomes a smaller value, a smaller fraction. So we are trying to keep the denominator as small as possible. How can we do so? By subtracting. So we subtract when we are moving towards, so that we end up having a bigger value at the on the fraction. right? It's one way of knowing so that we avoid to actually just memorize it in a certain way. But of course, if this is not making sense, of course, you can just know that when are you going to add and when are you going to subtract. It's still good to know that, right? So this marks the Doppler equation. So given now situations when the questions are coming now in the exam, you may be asked perhaps to calculate the frequency of the listener. It's now important to be able to depict from the given information which frequency is the frequency of the listener, which is the frequency of the source. So when we talk of the frequency of the listener, we are talking of the recipient of the sound, the one who is listening to the sound, or the observer, right? When we talk of the frequency of the source, we are talking of the emitter of the sound. Where is the source of the sound coming from? That's, of course, the frequency of the source. And apparently, that's also the velocity of the source, right? And the velocity of the listener, of course, it's in tandem with the frequency of the listener is where we are talking of the recipient. And of course, the V is the velocity, as we have mentioned, the velocity of the sound in air, the speed of sound in air, depending on which medium it's traveling in. Sound can travel in a vacuum. It can travel in different mediums, but usually you realize you'll be given take the velocity of the velocity of air of the sound in air as such and such. You'll be given the value, or perhaps you may be asked as well to calculate it. So this is our equation. This marks our equation.